Okay, so we'll be talking about exact differential equations and equations which are not exact and how to make them exact by finding an integrating factor. So we're talking about first order differential equations, and we're going to write them in differential form. So instead of writing them as dy dx equals some function of x and y, we'll be thinking of them in terms of some function of x and y multiplying dx and some function of x and y multiplying dy. And this is a total differential, and that's equal to 0. And you should be able to go back and forth between these two forms, these two conventional forms. So for example, starting with the differential form of our equation, we can move the dx differential part to the right, and then we can cross divide, so to speak. But when talking about exact differential equations, you might stick with this differential form. So the idea is that if, and from now on, I'm going to write m times dx, where it's understood that m in general is a function of x and y, and and n is a function of x and y. We're going to check whether this differential equation is exact. Well, the test for a differential equation being exact like this is to take the function that multiplies dx, the m in this case, and differentiate it with respect to y. So you take the m, which multiplies the differential dx, and you differentiate that with respect to y. And then you differentiate n, the thing that multiplies dy, and you differentiate that with respect to the other variable x. So if these are equal, then we can say yes, our differential equation is exact. The differential equation, or these two partial derivatives, are not equal for all x and y, then the answer is no, our equation is not exact. So let's look at an example. So suppose we have 2xy times dx. So we identify m as the thing that multiplies the dx, and we identify the n as the function which multiplies dy. So now we're going to take the derivative of m with respect to y and differentiate n with respect to x. And you see that in both cases we get 2 times x, so those are equal. So we can say our differential equation is exact. Now, on the other hand, we have another first order differential equation. So we identify m and n, and then differentiate m with respect to y, differentiate n with respect to x, and we see that these are not equal, so not exact. Okay, but why is it useful that our differential equation is exact? Why is that of interest to us? Okay, so imagine how a professor or somebody might come up, or you might come up with your own differential equation which is exact. You can start with a function of x and y. So we can start with a function of x and y, and then consider the level curve of that function, so set that equal to a constant. So we can think of this as an equation which has a graph in the xy plane, and that graph it's going to be a solution curve to a differential equation. So now compute the total differential on both sides. So remember that the total differential is where you differentiate your function with respect to all the variables times corresponding differential. So, and then on the right-hand side, the differential of a constant is 0. Right? So So we get this first order differential equation in a differential form like that, equal to 0. And then notice that the thing that multiplies dx we called n. So n is really the derivative of some big F function with respect to x. And n is the thing that multiplies dy, and it's the derivative of big F with respect to y. Okay. So when we do this test for exactness, remember that we differentiate m with respect to the variable y. So that's the same as taking a second derivative with respect to x and then y. And then when we differentiate n with respect to x, it's like taking the second derivative of big F, right? But first you differentiate with respect to y and then x. So notice the order is switched around here. The order of differentiation is switched around, right? Which, if your function happens to be smooth enough, so the function, if f is, if the second order derivatives exist and they're continuous, so we say f is c2, but it's neither here or there. But it's then we know that the mixed partial derivatives, second order partial derivatives, are equal. Okay. So when we test for exactness, we're taking advantage of the fact that mixed partial derivatives are equal. So these should be equal if our differential equation came from taking a total differential of some level curve there. So we're checking whether these are equal. And if they are equal, then the idea is to, starting with this, to be able to recover this level curve, right? To recover big F, which I forget the details, but I believe if it's sufficient that these two things are equal on a star-shaped domain in the xy plane, star-shaped region in the xy plane. All right, so sure. So once, suppose we know that our differential equation is exact because it passes the test, then how do we recover big F? Well, to recover big F, notice that the derivative of big F with respect to x is equal to n. So in order to recover big F, we're just going to anti-differentiate both sides here. We're going to anti-differentiate m, but with respect to x. So let's do that. Where we identified m and n, we found that the differential equation is exact. So the derivative of big F, which we don't know what that is right now, with respect to x, is m. So if you anti-differentiate both sides with respect to x, you should recover f. So this is kind of like an antiderivative, like a partial antiderivative, so to speak, where we treat y as a constant. So we y can even pull outside the integral because we're integrating with respect to x. And then, of course, this is x squared. Now, the key here is to remember that we get a constant of integration, except it's more than a constant. It's a function of the other variable. Let's call that function h. So it could be a function of the other variable, so h of y. And indeed, this is correct, right? Because if we differentiate f with respect to x, we should get back the thing we were just anti-differentiating. And remember, we're differentiating with respect to x. And here, h is just a function of y, so when you differentiate h with respect to x, you get 0. So indeed, that's the correct antiderivative. All right, now, well, have we recovered our function big F yet? Not quite. We still have this h of y. We don't know what that is. So how do we discover what that is? Well, we use the other piece of information. So notice that the derivative of big F with respect to y is equal to n, right? So if we differentiate big F with respect to y this time, Okay, so we recover f. We differentiate f with respect to y, and then we set that equal to n. So differentiate f with respect to y. You're going to get an h prime because h is just a function of variable y. So we have prime. I mean, I didn't have to write it that way, but it's understood that it's a derivative with respect to y. And that should be equal to n, where n is 2, x squared rather, plus 4y cubed. All right, so notice the beautiful thing. The x squares cancel out. And all the x's better cancel out because according to this, h is just a function of y. It's a function of just y. So h prime is going to be just a function of y. So you better just have y's left over, no x's, otherwise you get some sort of contradiction, an assumption. But now we can easily, I mean, this is a, if you'd like, it's a separable differential equation, yeah? But it's that's maybe overkill. And so just to get rid of the prime, just anti-differentiate both sides, and you get that h is y to the power 4. Okay, so now we can finally write our function of x and y, big F. It is y times x squared plus h of y, which we found to be y to the 4 power. And then the solution curve would be where this function, the level curve for this function, it's some arbitrary constant. This would be the solution curve. It's a general solution, right, because of that arbitrary constant. To summarize, we had a first order differential equation written in this differential form. You identify m as the thing that multiplies dx, and you identify n as the thing that multiplies dy. You check for exactness, so the derivative of m with respect to y should be this. It would be the same as the derivative of n with respect to x. And then we try to find a solution in the form of some function big F being equal to a constant. And we recover f by anti-differentiating m with respect to x, and we get a constant of a function of integration. And then differentiating that with respect to y, setting it equal to n, and hopefully this will allow us to solve for this h. This is at least one way to do it. So maybe we can do another example of the exact differential equation. So let's do another example. Here's a differential that's equal to 0. M is the function multiplying dx. N here is, if you notice, it's a minus cosine. It's a negative cosine of x. We check for exactness. So differentiate m, but with respect to variable y. And then you differentiate n with respect to variable x. Okay. So we see that, yes, indeed, these are equal. So we have an exact differential equation. And now we hope to recover a solution to this differential equation in the form of some function big F of x and y being equal to a constant. And remember that it turned out that the derivative of big F with respect to x was exactly m, right? The thing that multiplies dx. So this suggests that if we want to recover big F, we anti-differentiate both sides with respect to x. Okay? And we get x minus y cosine x plus, instead of that constant integration, we have an arbitrary function of the other variable. And then we take advantage of the fact that the derivative of big F with respect to y is what we call the n. So we differentiate big F with respect to y. And notice that the h is a function of y, so that's just h prime. We can set that equal to n. N is the negative cosine. And again, all the functions of x should go out. Now we get h prime is 0. It just means h prime is an arbitrary constant, right? But h of y is an arbitrary constant. So we can update our function, and we can say that f is x minus y cosine x plus some h of y, which is, we'll just let it be 0, and then the solution curve is the level curve for this function at c. Now, by the way, there is nothing stopping us from, instead of taking, first taking m, right, and anti-differentiating with respect to x, we could have switched it up, and then instead could have taken used the fact. So this is an alternative. So we know that the derivative of f with respect to y is n. So we can recover big F by anti-differentiating n with respect to y. So we get a negative sign. Oh, my bad. It's an antiderivative with respect to y. So minus y cosine x. And then we get instead of a constant integration, we get a function of the other variable. So here we're anti-differentiating with respect to y. So this must be a function of x. Let's call it g of x. All right, and now we can in turn, take advantage of the fact that the derivative of big F with respect to x should be m. So let's differentiate big F with respect to x. Okay, and that should be equal to m, where m is 1 plus y sine x. Okay, so notice the beautiful cancellation, and we get that g prime at x is 1. So anti-differentiating both sides, we discover that g of x is equal to x up to a constant. So let's update our final function, f, right? So we have f is equal to negative y cosine x plus g of x, which is just x. And so our solution curve is exactly this function, the level curve for that function, big F. Okay, so of course the question arises, as you've probably seen in class, what happens if the derivative of m with respect to y does not equal derivative of n with respect to x in our differential equation? That is to say, what if our differential equation is not exact? If it's not exact, then we can take advantage, we can try to find what we call an integrating factor. So suppose you do this test for exactness. So you have the derivative of m with respect to y, and then the derivative of n with respect to x. And these are not equal, so so our differential equation is not exact. Well, what if we could magically multiply both sides of this differential equation by a function, possibly x and y, so that it does become exact? So let's call this function of x and y mu. That's a new convention some people use. And this is called the integrating factor. And it's going to be designed so that when it multiplying the equation by mu, the integrating factor, we get something which is exact. And of course, on the right-hand side, mu times 0 is 0. So now we want this to be exact, meaning that the derivative of the thing that multiplies dx, the derivative of that with respect to y should be the same as the derivative of the thing that multiplies dy. That's like our new n, if you will. And differentiate that with respect to x. And hopefully they'll be exact, right? So I'm not going to say how to find the integrating factor just yet, right? And I said I was going to do an example without telling you of an exact differential equation. I was going to introduce an integrating factor to see how that would work without telling you how I found the integrating factor. We can worry about that next. Identify m as the thing multiplying dx. Identify n as the thing multiplying dy. Check for exactness. So differentiate m with respect to y. Differentiate n with respect to x. And notice that those are not equal, right? 1 is not equal to negative 1. Therefore, not exact. My claim is that if I were to multiply both sides by 1 over x squared, this is going to be my integrating factor. And again, I'm not telling you how I got it. I just want to show that it works if you're able to find this integrating factor. And its job is to multiply both sides of the original differential equation by 1 over x squared. Its job is to multiply both sides of the differential equation so that it does become exact. So you multiply both sides by 1 over x squared. All right, so now let's check. So our new m, so let's just call this m tilde, differentiating that with respect to, now I'm just using a tilde on the m just to distinguish it from the original, distinguish that from the original m. Okay, so no big deal. You can call it m again if you'd like, without, if that doesn't throw you off. So we're going to differentiate m tilde with respect to y. So n tilde, if you will, is 1 over x. So the derivative of n tilde with respect to x would be negative 1 over x squared. So indeed, these are now equal. So we see that our differential equation here is exact, meaning that we can try to recover some function, big F of x and y, whose total differential is equal to this left-hand side. And if we set that equal to a constant, that's going to give us a level curve representing a solution curve to the differential equation. The derivative of this big F with respect to x is the m, or in our case, the m tilde. So we can recover big F by anti-differentiating with respect to x. Okay, so that's x plus y over x minus x cubed. And then we get a function of the other variable y. And then we take advantage of the fact that the derivative of big F with respect to y should equal to n tilde. So we differentiate our big F with respect to y. And we get 1 over x plus h prime. And that should equal to n tilde. So that's 1 over x. Indeed, 1 over x is canceled. And you get that h prime is just 0, so h is a constant, an arbitrary constant. All right, so finally we get that big F is given by x plus y over x minus x cubed plus h, which is just, to make it 0, we set that equal to a constant. And this would be, well, so this is our function, and this solution curve is a level curve to this function. So the question is, how do we find this integrating factor? Is it unique? Well, it's not unique, and it's not necessarily easy to find. But let's see. But because the integrating factor is not unique, maybe we can make some simplifying assumptions about what the integrating factor is like to make it easier to find. So remember what we said, that if a differential equation is not exact, then we multiply everything by some integrating factor so that it does become exact. And now when differentiating, we're going to differentiate with respect to y on the left using product rule. So the derivative of mu with respect to y, m, plus mu times the derivative of m with respect to y. And then you differentiate the left-hand side with respect to x using product rule. So now let's to find integrating factor mu, we're going to try to make some simplifying assumptions. So for example, let's assume, so the first case is that, let's assume that the integrating factor is just a function of x. It's a function of x only, not y. So that's just an assumption, right? And so in particular, what that means is the derivative of the integrating factor with respect to y must be 0, because mu is just a function of x. Hence, this term would go away, right? What we have above would reduce to, because the first term would go to 0, mu times the, so now I'm just going to bring all the terms that have a mu in them to the left. Notice then in that case, mu is a common factor, so you can factor that out. I'm going to write mu sub x as the derivative of mu with respect to x. And then you notice that then this differential equation is separable. Well, hold on. Let's bring all the mu stuff to the one side, and everything that doesn't have a mu in it to the right, to the left. Okay, and let's just inspect that, right? So what we have is that 1 over mu d mu. We assumed that mu is just a function of x only. Meaning that if that assumption is to be true, it would have to be the case that the opposite side equal to, or the side that's equal, this has to be a function of x as well. Otherwise, we have some sort of contradiction. So if this expression is a function of x and no other variable, then the assumption that 1 over, the assumption that mu is a function of x is valid, and then we can just anti-differentiate both sides here to recover mu. And then exponentiate, and then you have a formula for the integrating factor, for a integrating factor. But for this to work, remember, this condition has to hold, right? So let's go back to our previous example to see how I might have found that integrating factor. All right, so here's our original differential equation that we just visited. And I told you what the integrating factor was. It was 1 over x squared. Now, we found that this differential equation was not exact. But then notice that if we simply try seeing whether our integrating factor is just a function of x, we would have to make sure that this expression is a function of x only. So n is x. Indeed, that's a function of x only, meaning that there exists an integrating factor, which is just a function of x, and it's given by e raised to the antiderivative of this expression. I want to assume x is positive here. Yeah. So the integrating factor is 1 over x squared. So that's how I got the integrating factor, by assuming it's a function of x. I checked whether that assumption is correct by checking whether that expression is just a function of x, and it was. Then I used my formula for this integrating factor. If sometimes assuming that our integrating factor is just a function of x works, sometimes, can we assume that mu is just a function of y to see if that works? Absolutely. So let's try that. So let's look at what conditions would have to hold for our integrating factor to be a function of y. So again, we have some inexact differential equation. Multiplying it by some integrating factor, not yet known, should make the differential equation exact. So differentiating with respect to y here should give you the same thing as differentiating with respect to x here. And then we used product rule to actually differentiate. Okay. So now let's assume, let's try to, because assumption can be wrong, right? So let's just try to find an integrating factor is just a function of y only. Yeah? Well, in particular, notice that if mu is just a function of y, then the derivative of mu with respect to x would be 0. So this term would go away. Okay? Bring all the terms that have a mu in them to one side of the equation. And I'm going to rewrite this is the derivative of mu with respect to y. Dividing by m, we get a separable differential equation. Okay, so now we said that mu is a function of y. So if that's true, the right-hand side should also be a function of just y. If this expression is a function of y only, then we can solve this differential equation for mu, and we get that our integrating factor is a function of y given by this formula. So let's see that in action. So we identify m as the thing multiplying the x, identify n as the thing multiplying dy. Check for exactness. So these partial derivatives are not equal, so our differential equation is not exact, meaning that we can try to find an integrating factor, which after multiplying our equation on both sides, we would get something that is exact. Here I'm going to make a simplifying assumption that our integrating factor is just a function of y and see if that assumption works. Right, so remember that for that assumption to work, that we have to check whether this expression is a function of y only. So let's see what that expression is. The derivative of n with respect to x minus the derivative of m with respect to y, all divided by n. Well, that doesn't look hopeful. Let's see. I can take out a minus 2 times x. So that's going to be 3 plus 2y. Oh, okay, my bad. So this is m. So I messed that up. Okay, so let's start that over, right? So I said that, so I made a mistake, this should be m. And so if this expression is a function of y only, then we can find an integrating factor, which is a function of y only, according to this formula. So for the assumption that mu is a function of y, to work, we see that this expression would have to be a function of y only. So we're going to pick up from here. Okay.
I am sorry, what is the writing center?
So we're checking whether this is a function of y only. I guess in the denominator, notice that I can factor a 2yx out. In the numerator, it's factor out a negative 4x. Indeed, we have some cancellations. Our expression is a function of y only. So we can find an integrating factor that's a function of y only. It's given by the formula e to the antiderivative of this expression with respect to y. So apparently, if we now multiply both sides of our differential equation by this integrating factor, it should become exact. So let's just double check. So our new m, or m tilde if you wish, and its derivative with respect to y. And then our new n, or n tilde, we're going to differentiate with respect to x. And indeed, these are equal, so we have exact equation. So now remember that the derivative of, we're looking for a curve, solution curve. Our solution is a level curve here of some function big F, and the derivative of big F with respect to x should be m tilde. So we're going to recover f by anti-differentiating with respect to x. And instead of a constant of integration, we get a function of integration, which is a function of the other variable, y. Now we're going to take advantage of the fact that the derivative of f with respect to y should be n tilde. So let's differentiate big F with respect to y. And we get, setting that equal to n tilde, sorry, setting it equal to n tilde. We have a nice cancellation, and we see that h prime is 1, so h must be y up to a constant. So now we can update f. F is x squared plus x squared divided by y plus h of y, which we discovered was y. And so the level curve, or level curve of this function is a solution curve to the differential equation. Do we have time for one more? Right, so remember that so far we said that it's not easy in general to find an integrating factor for a non-exact equation, but we have two special cases so far where if this expression is a function of x only, then we can find an integrating factor which is a function of x only according to this formula. And we derive that. It's just a result of a simple separable differential equation. Now the other special case was if the following expression is just a function of y, then we can find an integrating factor which is just a function of y according to this formula. And there are other special cases, but I guess how in general would we approach such? So if your professor said, well, I'm not going to tell you what a good integrating factor is for this problem, but I will tell you that it's a function of this sort. So how do we then approach finding an integrating factor for something novel like that, not one of these two standard special cases? Well, it starts with, again, knowing that by multiplying an inexact differential equation by an integrating factor makes it exact. Right? So that's always the starting point, meaning that these partial derivatives, so with respect to y on the one hand and with respect to x on the other, they should be equal, because we want exact, yeah? And then use product rule. So this is always a good starting point, finding integrating factor. So let's do an example where I tell you that there's an integrating factor, and it's a function of something novel, like say x times y. Yeah. So let's look at this differential equation. Okay. And now this differential equation is not exact. So m is what multiplies dx. N is what multiplies dy. Differentiate m with respect to y. Differentiate n with respect to x. So these are not equal, right? It's not exact. So we're going to find an integrating factor, but what I'm going to tell you is that the integrating factor is a function, call it v, of x times y. Now, if I tell you such an integrating factor exists and you look at the differential equation, you might guess what the integrating factor is. Okay. But how would you actually, using this assumption, how would you find the integrating factor? Well, notice that the derivative of mu with respect to x is, you have to use chain rule, so that's the derivative of this function. Let's suppose this is a function of z, right? Where z happens to be x times y. So when we differentiate phi with respect to z, it should be, with respect to x, it should be a chain rule. So we differentiate phi with respect to z, and then multiply by the derivative of z with respect to x. Hey, what's going on?
Hello, I'm here for a writing session.
I'm doing differential equations. So where are you supposed to meet? Where are you supposed to meet?
MC and this number.
Oh, what time?
12.
Oh.
Did anyone else come in?
Well, 2 people, but I sent them downstairs because that's where the writing center is.
Oh, okay.
Yeah, I don't know. I'm here till 12:15, so
Okay, thank you. I'll probably
Right.
visit. Do you know where the writing center is?
it's in the basement.
Like where the
You go down.
coffee shop is?
Yeah,
Okay.
Lemma. You go past Lemma, straight down that long hallway that's on your left.
Okay, thank you.
Just ask somebody if you.
All right.
And the derivative of z with respect to x is just y. So this we can write as phi prime of x times y, or z if you'd like, times the derivative of z with respect to x. So that's just y. And on the other hand, the derivative of mu with respect to y, again, differentiate this function with respect to its variable, and then use chain rule and multiply by the derivative of z with respect to y. Where the derivative of z with respect to y is just x. So now, you go to this general form and fill in the particulars, right? So we're going to have the derivative of mu with respect to y, just call that phi prime times x times n, x times m times phi prime, and then mu. And then mu, the derivative of mu with respect to x. So let's write that as y, n, and phi prime. Okay, gather all the terms that have the phi prime in them on one side of the equation. So that way you can factor out a phi prime. And gather all the terms that don't have a phi prime. And notice that mu is phi, if you will. Factor out mu, but mu is phi, so we can, phi prime, by the way, we're going to write as the derivative of phi with respect to z. We'll then bring all the separate, so we'll write 1 over phi d phi should be the same as, if you remember what z stands for, it stands for x times y. So for our assumption to be correct that mu is a function of x times y, this expression has to be a function of x times y. So, or z, in other words. So let's check. Okay. So we have partial then with respect to x minus the partial of m with respect to y. Then x times m minus y times n. Simplifying this, the numerator, you can choose a common factor. The exponential is a common factor, and you're left with x squared plus y squared. On top, bottom, these guys cancel. Again, you can, nice. So indeed, in a trivial sense, this is just 1. So in a trivial sense, this expression is just a function of z, right? It's a constant function. So then we have 1 over phi d phi is equal to dz. So we anti-differentiate the two equal differentials and then exponentiate. So an integrating factor would be some constant times e to the z, where z is equal to x times y. And now it's any constant, you know, so I'll just choose, k is an arbitrary constant, I'll choose k to be 1. So the claim is that this is a good integrating factor. So it should make this differential equation exact after we multiply both sides by the integrating factor. This is our new m. Differentiate m tilde with respect to y. Differentiate n tilde with respect to x. Indeed, these are equal. We have an exact differential equation. So the derivative of, we're looking for a solution curve, which is the level curve of some function, big F. Derivative of big F with respect to x is n tilde. So we can recover f by anti-differentiating m tilde with respect to x. So then differentiating big F with respect to y should give us n tilde. So set that equal to n tilde. We're doing these well. These cancel, and we have that h prime as a function of y is just negative 2y. So h prime must be minus y squared up the constant. So now we can update f. Our function of x and y, big F, is equal to this business, and then we know h of y is negative y squared. And our solution curves are level curves of this function. All right, thanks for joining me.